Good morning, everyone. My name is Eric Shakti. Today I'll be giving you a presentation about torque and tension. Today we're going to do a little bit of math. We're going to ask you guys a few questions. It's definitely an interactive presentation. And we're actually going to see some hands-on demonstrations from my friend Nathan over here. So our objective for today is to learn about torque and tension. A lot of people have a good understanding of what torque is and maybe a little bit different understanding of what tension is. So we're going to discuss the relationship between the two. Now, why do we care about the relationship between torque and tension? How is that important to anyone in this room? Any ideas?
Well, I'm thinking that torque relates to tension because you use torque to get tension in a joint.
That's true. That's one of the reasons. So, by understanding torque and tension, what it's going to allow us to do, it's going to let us promote better designs from the beginning and help reduce the amount of errors and the amount of quality issues we have down the line. Everyone in this room, or most of us, are all engineers. We like to get our main work done of designing new products. Nobody wants to go out to a production line or wants to go out to a customer's location when a joint fails or a fastener breaks or other issues like that. So that just causes delays and wastes time. So by understanding torque and tension from the beginning, we can all make better designs and we can design products correctly, and save time in the future. Now, the agenda today is going to be a pretty full schedule. We're going to discuss some things about the relationship of torque and tension. We're going to do a little bit of math here and there. Like I mentioned, Nathan's going to do some hands-on presentations as well. So here we have a diagram of the bolted joint. Can anyone tell me what's the purpose of a bolted joint? What do we want that joint to do? Brendan?
Hold two things together.
Okay, that's good. What type of forces act on a bolted joint? If you've got a bolted joint in service holding onto a bridge or holding a car frame together or something like that, what forces would you see acting on that joint? How about what direction would you see the forces?
Well, there'd be this way and this way.
Exactly, correct.
Shear.
The joint's got to withstand, generally, the two main forces are your shear strength, or shear forces, which, like Brendan mentioned, go left to right, and your tensile forces, which are up and down in this direction over here. What if we welded the joint together or used an adhesive? How would that be better or worse or different, or how is that different than a bolted joint? Any ideas? Well, if you had a welding or an adhesive joint, that's a static joint right there. A bolted joint like this is a dynamic joint, where you've actually got the tension in the joint helps to withstand these forces right here. And the way that, what I mentioned here, the way that they withstand these forces is through clamp load right here. So this is actually a dynamic joint. Whereas if you had a static joint, like a welded joint or an adhesive joint, you're relying on the bond to withstand the forces. In a dynamic bolted joint, you're allowing the clamp load to help resist these forces. So go through a couple terms right here. First, we've got clamp force, which is the compressive force extended between the mating surfaces of the joint. We've also got preload. Preload is the amount of tensile force in the fastener at assembly. Now, this is a little bit different because this does specify this is at assembly, correct, right here? So the amount of tension in your joint is only at that point in time. What happens to your preload, or what happens to your clamp force over time in the joint? If you start out with a joint and you clamp it down to 2,900 pounds of force initially, what happens to that force over time? Does it increase or decrease or stay the same? Or?
Decrease.
Yep. And generally it does decrease. And that's always due to joint relaxation or embedment and other factors like that. It really cannot be eliminated. You have to design for it in your design that you're going to lose clamp force. So our third term is tension. And tension is the axial force on the fastener in the bolted joint. And your tension on your bolt is always equal to your clamp force right here. Tension on the screw is pulling this direction, creates a force of clamping in the joint. What are some of the units of these three measurements right here? Would that be a length measurement, or would that be time measurement, or?
Pounds.
It would be pounds. It would be something like a pounds of force or a PSI in some cases. So, some other terms, we have tensile strength, or UTS for ultimate tensile strength. And this is the maximum load that a fastener can withstand. We've got the yield strength, which is the load at which the fastener is permanently deformed. And then finally, we have the proof load, which is the load that a fastener must withstand without any permanent deformation. So these are related to the fastener itself. Of these three readings, which one's highest, which one's lowest, which one's in the middle? Phoebe, any ideas which one would be?
I would guess the highest will be the yield.
The highest would actually be the tensile strength in this case, because this should be when the fastener, the maximum load when the fastener would break right there. So generally, you're going to hit your proof load first. This is your load with you can stretch the fastener and it'll return to its original shape. The yield strength is when you put a load on it and it actually stretches. It does not return to its initial shape, but it has not fractured yet. It's still one continuous piece. And then your tensile strength is actually when the fastener is fractured. And again, these are all measured in pounds or PSI. So we take a look at a little graph here. This is a fastener tensile test graph. The way you can read this here is on the right side, on the y-axis, you've got your stress. On the x-axis, you've got your elongation down here. So the way you read this is that as your stress increases on the joint, your fastener elongates and stretches along here. So we've labeled 3 points, 1, 2, and 3. Can anyone name what these points are? Which one would be your ultimate tensile strength on this graph?
Point one. One.
Number 1, correct. Yes, 0.1 would be your ultimate tensile strength. This is the highest amount of stress this fastener has seen, right here. What would 0.3 be? What happens at this location where the graph just stops right there? Randy?
That would be where the fastener failed or the joint failed.
Okay. Okay. And by process of elimination, what would that make 0.2 then?
So would it be a fastener or joint failure then?
It could be either in this case right here. You've got some failure over there. Well, I'm sorry. And the tensile test in this case, this would be fastener failure.
So what's the difference there?
Between fastener failure and joint failure?
So how does this not apply to the joint?
This is just a straight tensile test. We're not actually assembling a joint in this test. The way it works is your fastener is assembled in a fixture. It's stationary on top. It's got a hydraulic ram on the bottom that actually pulls the fastener in the axial direction. And it measures the amount of force it takes to stretch that fastener and the amount it stretches right there. So this is actually not a bolted joint. This is more of it's a tensile test is what it is. It's used by heat treaters and other manufacturers to determine is this bolt meeting the specifications, the strength specifications. So you're correct, this is not actually a bolted joint. So on this graph, that would mean our 0.2 is the yield point that's left over. So this point here, you can see on the curve, you've got your straight line here is your elastic region, where if you were to take the bolt up to any amount of stress in here and then release it, you're going to return back to your original length right here. Once you get to 0.2, where the bolt starts to yield, you've put so much stress in here that this bolt is actually stretching at this point, and it's not going to return to its original shape, or original length right there. On the last slide, we talked about proof load a little bit. Where would proof load be on this graph? Or why didn't we put a point for proof load? Randy?
Proof load is right before your yield strength, and I think it's kind of hard to determine. It's normally, what, 70 or 80% of your yield?
In general, that's a good rule of thumb. Proof load isn't something that you can actually measure on a fastener. It's something that's specified out in the specification. If you wanted to, you can make your proof load here, you can make your proof load here, 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 anywhere on this line, more or less. It's just saying that this fastener has to withstand this load for this period of time, or 15 seconds, or whatever the time is, and then return to its original length right there. So your proof load could be anywhere along this line. But generally, like Randy said, you're going to have about 80% of your yield strength right about here. So they try to get it as much up the elastic region as possible. Now, a screw is a simple machine, and there's two different types of screws, or two different types of uses for them. In this case, the screw can be used to turn rotational motion into linear motion. You see items like this on a lead screw that you see like on a lathe or a mill, where you'd actually rotate the fastener or rotate the screw right here, And it would cause this carousel to move back and forth right there. For our cases, we're going to be using a screw in a different way. We're going to be using it to convert rotational force to linear force. When you put a wrench on the head and you rotate that screw, you're going to turn that rotational force into a tension force. And a thread is essentially an inclined plane wrapped around the cylinder. So when you're tightening the screw, this is a graphical representation. You're actually trying to take this block and push this block up this inclined plane, which is essentially what your screw thread is. Now, people often say that a bolt acts like a spring. Is that you're going to stretch the bolt, you're going to keep the clamp load in your joint. And it's going to act the same way a spring would act. And it's very true. So we can see here on the right side, here's a spring. This is Hooke's law over here. Now what this is, these variables, your F is your amount of force necessary to stretch this spring. K is your spring constant. That's how stiff the spring is. X is your distance of extension. So if you were to stretch the spring by half an inch or quarter inch or 20 thousandths, whatever you're going to stretch it by, this would be the formula you would use right here. So again, it's just force equals your spring constant times your length. So it's a fairly simple formula once you know these numbers here. With the bolt over here, we use the same kind of formula, only with a slight difference. Again, we've got the big F here is the amount of force necessary to stretch the bolt. We've got an X here, same as the X over here. It's the amount of stretch you're going to put into this bolt, and it's a length if you're going to stretch that bolt 10 thousandths, 15 thousandths, whatever that's going to be. But then we've got some different variables over here. We have E times A over L. This here is equivalent, or it's accomplishing the same thing you would do with the spring factor on this graph over here. Your E is your Young's modulus of steel, which is a measure of the stiffness of the steel. A is your screw area. L is your clamped length right there. So these three terms gives you the stiffness of the joint, and it's roughly serves the same purpose as the K in this formula here. So
What do you use for A?
it's a good question. A is the area of the stress area of the thread. So if you've got a 1/4 inch screw right here, you wouldn't use a 1/4 inch as your A. You actually use the stress area of the thread. But that does change a little bit because if you've got a clamp length, so if you imagine your joint goes from here to here, you've also got this shoulder in the joint. So in this case, you'd have to redo the same calculation, but use this diameter for your A over here. So if you've got this fastener, for instance, again, clamp length from here to here you're clamping, you have to do this calculation twice to figure out what this is going to stretch and what your shoulder is going to stretch. That's kind of why you see a lot of the times in real critical bolts, you see on connecting rods and in engines, where you'll see the kind of a neck down portion underneath the head where there's no threads. They do that for this reason right here. When they actually shave this down and make this smaller in those kind of applications, what they're doing is they're making this A number right here constant throughout the fastener. So you get one consistent or one constant amount of stretch, as opposed to this way where you get two different amounts of stretch right there.
So, the A is basically, it's about the pitch diameter of the thread. Is that what it is?
It's a stress area, which is actually a little bit less than the pitch area, the pitch diameter of the thread. The stress area is something that was calculated through experimentation. It's roughly halfway between your pitch diameter and your minor diameter. So in this case, this really shows you that your amount of your stretch, or how stiff your fastener is, really depends a lot on your geometry. Again, the area over the clamped length right here. What would have happened if we were to take this clamp length and double it? What if we made this instead of 1 inch of length? What if we made this 2 inches right there? What would that do to our formula that's over there? Nathan, any ideas?
It would increase the amount that it stretches at a given force.
It would. What Nathan said, if you couldn't hear, it would increase the amount of stretch if you're to keep your force the same right there. So if you were to go from 1 inch of clamp length to 2 inches of clamp length, keep your force the same, your stretch may go from 5 thousandths to 10 thousandths. And again, we learned in previous seminars that the more bolt stretch you have, in general, you've got a more robust joint that it'll withstand the forces of relaxation and bending much better. In general, you want to have as much stretch in your fastener as possible. So now we're going to talk a little bit about torque and what that is. A lot of us have a good idea of what torque is. In pretty simple terms, it's the force times your distance. So if you look at our wrench over here, if we have 20 pounds of force at 3 inches long, that equals torque right there. But the same number is equal to 10 pounds of force at 6 inches right there. So you'll double your length from the center of your bolt. The force required takes half as much to rotate that. So generally, what we count torque in foot-pounds is one method right here. How many foot-pounds of torque would that be? Brendan, any idea?
Would be 60.
It'd actually be 5 foot-pounds, because you'd be doubling your length to 12 inches for 1 foot would only require 5 pounds of force. So actually, and I'm sorry, 60 inch-pounds is what that works out to be. So, which is 5 foot-pounds. So torque is a means to an end. Now, what does that mean exactly? When we go to put a joint together, is torque actually holding the joint stiff, or is that what's keeping that secure?
Torque creates the
Exactly. The goal is to create clamping force. Clamping force, like we learned earlier, is what holds your joint together. It's what resists your forces in the shear direction and in tension forces. Again, we stretch the fastener. That's the way we obtain this goal. And then the means to stretch the fastener is through torque. That's our general, easiest, most common way to stretch a fastener. There is other methods. There's hydraulic tightening. There's other less common methods of stretching a fastener, but for most industrial applications, the most simplest ways, torque is the most cost-effective way to accomplish that. So again, just to explain the torque-tension relationship, kind of in basic, simple terms, we're going to add a rotational force to the fastener, either through the head or the nut. That's going to create an axial force in the bolt. And what's that going to do? That's going to create clamp load in the joint. And again, your axial force is equivalent to your clamp load right there. So my friend Nathan over here is going to do a little hands-on demonstration.
All right, I will be testing a 1/4-20 grade 5 zinc-plated hex cap screw on our equipment, which simultaneously measures the torque in the nut and the tension in the bolt. Okay, so we get a graph that shows the yield point of this grade 5 hex cap screw, and it looks like it yielded right about 150 inch-pounds of torque and 2,700 pounds of clamp.
So if we were to graph that, at one point Nathan got, you're right about there. So if we show that graphically, so here's a graph of what Nathan just showed right here. Again, we're going to have our torque on the x-axis, our tension on the y-axis over here. We'll have our yield point roughly here, our ultimate strength over here, and our fastener failure right here. Nathan didn't take this obviously to failure, but if you continue to torque it past the yield point, you see a graph similar to this. So now if Nathan were to do this part was a grade 5, if you were to do a grade 2, which would be less strength than a grade 5, or a grade 8, which would be stronger, where would that line fall on this graph? If you did a less strong screw and a stronger screw. Any ideas, people? If you had a grade 2 screw, which would be weaker. Would it be down here? Would it be above the line? Would it be on the line? Okay. You do a little demonstration. Brendan, if we had a grade 8, where would that fall? Stronger screw.
higher.
Okay.
So can you draw the grade 5 and illustrate the big make? So what are the predictions?
Brendan said the grade 8 would be higher. Phoebe said the grade 2 would be lower. So now we'll see what what Nathan gets in his results.
Okay, first one we'll test is a grade 2. So this one yielded at 120 pounds of, or 120 inch-pounds of torque and 2,500 pounds of flange.
There.
And this is the grade 8. The grade 8 yielded at 200 inch-pounds of torque and 3,700 pounds of flange.
If we draw a best fit line for these 3 points, you kind of see that they're roughly all on the same slope right here. One actually hasn't fallen above or below the line. You can actually illustrate that. Right here. Again, it's the same torque tension graph. We've got a grade 5, grade 8, grade 2 fasteners. They all fall along the same line, or the same slope line in the elastic region. The only difference is where your yield point starts to break off and you go towards ultimate tensile strength in all 3 of these right here. So why that's important to us is it shows us that no matter what your strength rate of your fastener is, a steel fastener, assuming nothing else has changed, in this case, for example, you'd have 100 inch-pounds of torque, you'd have roughly 1,500 pounds of clamp load, no matter which fastener you were to choose right here. So now we're going to move on to a little bit of math right here. So I hope you all brought your calculators like I asked. Everyone's got those? We don't need calculators. This first graph right here, what we're going to do here with this graph, our ultimate goal is right down here. This is the amount of torque needed to preload the fastener. That's your T sub P right here. So this is how much torque is needed to stretch that fastener. The math looks very complicated, but I'm going to step through it real quick, and it's a lot simpler than it looks. So we start out with the top up here. F is the force required to rotate the fastener. P sub B over here is the amount of preload we're looking for in the joint. Preload we need in the joint we can find on rules of thumb or other charts right there. You generally want 75% of your yield strength, so this variable here, we can determine that from charts or from other testing. And again, you do multiply that by tangent of theta, which is your helix angle down here. Another way to calculate it as well, see it equals over here, equals your pitch over twice the diameter. Your pitch being your thread pitch, your diameter being the diameter at the pitch diameter of the fastener. So pitch is easy to determine. For a quarter 20, it's 50 thousandths of an inch. Your diameter is also easy to determine. You can look that up. It's about 215 for a quarter inch. So while this equation looks kind of complicated, the variables are pretty straightforward. So once you know those, it's relatively plug and play. So once we know our force required to rotate that fastener, we plug that into this formula down here. And again, this is the torque required to preload the joint, or the torque required to stretch the joint, multiplied by the force we just figured out, times the radius of the fastener right there. Now we learned earlier that torque is force times distance, which is exactly what we're doing right here. Pretty simple terms. Again, your radius of your fastener is easy to determine. That's not anything that's too complicated right there. And that's really your whole equation right there. This would be the expanded version of this, if you were to put it to the right equal sign over here. If you simplify this, you end up with this equation down here. So your torque required to preload the joint is equal to the preload you're looking for multiplied by the pitch over 2 times pi. So with all this math right here, it actually works out to be relatively simple and relatively straightforward. So what we'll look at is an example of this. Again, the quarter 20 grade 5, which is what Nathan was testing. Like we mentioned, 75% of yield is about 2,200 pounds of force. So if we plug that into our equation, the torque equals the 2194 pounds of force multiplied by your pitch, which is just 50 thousandths, over 2 pi. So again, that works out to your torque required to stretch that fastener at 17.5 inch-pounds of torque. Now, what do you think of that number? Does anybody think that's a fair number or a round number to stretch that bolt? That's about 1.5 foot-pounds of torque.
That's kind of low.
I think that's a little low too. So, what's missing from this equation? So, if this is the formula, and this is all the math of what it takes to stretch that bolt, how come this 1.5 foot-pounds of torque isn't what we would use to assemble a joint? What's missing from here? Any ideas?
I think there's friction would be something.
Yep, absolutely. This formula here doesn't take friction into account at all. This is just pure to rotate that bolt to stretch it out. Friction isn't in this formula. That's why this number is much lower than you would normally use in real life. So here's a picture of our joint. What 2 areas would create friction when you were assembling this joint? If you were going to turn this nut on the bottom, where would you create friction? Phoebe, any ideas? What would rub together in this joint if you were to tighten that down?
The washer base.
Yep, exactly. Where else? Anywhere else that would kind of have 2 surfaces rubbing together?
On the bottom would be the nut.
You would see 2 things. You would see the washer face, because generally the bolt's going to stay still, but your nut would rotate, or vice versa. But your 2 areas of friction are in your threads, and then in the bearing surface right here. If you were to tighten the head of this fastener over here, you'd still have your thread friction, that wouldn't change. But then this friction here would actually change to be up in this area here, because this would be stationary. So generally you're going to have friction in those 2 areas. So we need to determine how much torque is needed to overcome that friction right there. If I create friction, you need force to overcome that force that's acting against it. So we're going to figure how much torque is necessary to overcome thread friction. That's what you see out here. Again, you've got T sub Ft is the torque required to overcome the friction in the threads. That's what this means right here. That's what we're looking to do right here. Again, if we look up top and kind of break this down, it's a lot simpler than it looks. Your P sub n over here is the amount of preload that's perpendicular to the threads. So the way we figure that, again, P sub B is the preload you want in the joint. Again, it's 2,100, 2,200 pounds in this case right here. Again, it's easy to look up by charts or by other testing. We're going to divide that by cosine of B. B being half your thread angle. We know that machine screw threads are 60 degrees, so your B is 30 degrees right here. So this formula here is relatively straightforward, not too difficult. So once we know this value, your P sub n, we substitute that in down here. Here's the force to overcome friction in the threads. Your U sub T is your coefficient of friction. Again, this comes off of charts, generally dependent on the surface finish. If you've got a slippery joint with a lot of oil, you'd have a much different coefficient of friction than if you had a rusty bolt, you'd have a lot more friction. So this variable here is determined generally from charts or from empirical testing. We determine what that actually is. So we multiply our coefficient of friction times our P sub n, which we just determined in the first formula, gives us the amount of force to overcome that thread friction. We then take that number here, plug it into our torque formula. So again, this is the torque required to overcome thread friction. Torque equals distance times force. We've got our force, we've got our radius of the screw, which is our distance. So again, this formula works out to be relatively straightforward as well. And again, if you simplify all these numbers, you come up with this formula down here. Now we look at bearing surface friction. And again, the ultimate goal here is to look for the torque required to overcome bearing surface friction. So if we start at the top again, the force required to overcome the bearing surface friction. Again, we've got a U sub B, which is your coefficient of friction, again, determined from charts or from testing, multiplied by your bolt preload, again, comes off of charts, so this is pretty straightforward. Once we have this value here, we plug that into our torque formula. Again, force times distance gives us our torque over here. And this would be the long form of this. The R is a little bit different in this case right here. It's actually the distance from the center of your bolt to the center of your bearing surface right here. And that's kind of displayed here is your dW plus dH divided by 4. Your dW being your washer diameter, your dH being your hole diameter. And the way to think about that is if you've got a really big hole diameter relative to your washer diameter, you've only got a little bit of bearing surface right here to create friction. Versus if you've got a tight hole and you've got a real long distance here, it's going to create more friction. So what your R does and what this part of the formula does down here is determine, again, from your center of your bolt to your center of your bearing surface. So it takes the geometry into consideration with this as well. So our full torque formula, torque required to preload that joint, is the first variable. You add that to the torque required to overcome thread friction, and you add that to the torque required to overcome bearing surface friction. A plus B plus C gives you your overall torque of what you're going to need to assemble that joint. And if you non-simplify this, you put all your variables there, you come up with these big long formulas right here. So if we do a little example, again, we'll look at the quarter 20 grade 5 cap screw that Nathan was testing. We've got our P, which is our pitch, which is 50 thousandths of an inch. Our diameter is 215, which is roughly the pitch diameter of the part. B is our half of our thread angle. Our DW is our washer diameter, so in this case it's 433. Our diameter of our hole is 266, because it's going to be a clearance hole for a 1/4 inch fastener. So we've got a little bit of clearance room between the two. And then our coefficient of frictions of both the thread and the bearing surface. Generally, in most cases, the coefficient of friction is the same in the two, because they generally have similar surface finishes with similar platings. So in this case, it's 0.17 for both of these. And now, if we do all this math right here, our torque is 129 inch-pounds. It's a lot different than the 17.5 inch-pounds we found originally right there. Now, what's alarming or what's surprising about these numbers here? Here's where it's broken down into torque to preload, torque to overcome thread friction, torque to overcome bearing surface friction right here. What do you notice about these numbers? Phoebe, any ideas? Or how do they look? I mean, are they similar? Are they really different? Or
Yeah.
you kind of see that this one's real small. This doesn't take much torque at all. Versus these two are much greater. And as a percentage of your ultimate torque, or I'm sorry, your assembly torque versus this, the torque to preload the joint isn't very much. So what that goes into is the old rule of thumb that a lot of people talk about, that 100% of your applied torque on every kind of fastener, 55% goes into underhead friction, about 1/3 goes into thread friction, and only about 10% goes to stretching that bolt and creating clamp load. So there's a lot of waste in the joint. Not waste, but a lot of the force you're exerting isn't going to where it's helpful to you. The friction here, in this case, doesn't necessarily create clamp load. So how does that help us? What does that mean for us? That's just a lot of math. We just want to see, if you're all going to sit here, how does this help me in my everyday job right here? What if you're working on an assembly line, or you're an engineer at a certain place, and you run out of these quarter 20 cap screws right here? Well, you look for a substitute or something else you can use. Let's say you've got this hex flange screw that you can use. Can you just take this screw out and just replace it with this and not change your torque or not change anything with that? Nope, you can't. And the reason for that is because of D sub W is your washer diameter, or your bearing surface diameter. Your DW2 is your bearing surface diameter here. These numbers have changed. If we were to plug those numbers to our formulas we just reviewed, but again, if we were doing the wrong thing, we would keep the torque the same, 129 inch-pounds. 129 inch-pounds. We had two different amounts of clamp load. This is the preload and the bolt. From our goal of the 2,194 pounds, it'd be reduced to about 2,000 pounds of clamp load, just by changing that bearing surface. And that's assuming that everything else is the same, the plating's the same, there's no other changes to the joint at all. So the correct way to do this would be, yes, I can substitute this hex flange screw right here, but I do adjust my torque to compensate. So again, we've got our new washer diameter. We know our preload we want to aim for. We redo our calculations, we learned that the new torque to use this part is now 140 inch-pounds. So Nathan's going to do a demonstration now. What do you think would happen if we were to use like a serrated bearing surface or a real rough bearing surface?
Would be higher.
Let's see what Nathan's got over here. So Nathan's got a serrated
Try it
bearing.
out, will you?
Yes.
So something would change.
So, you want to draw it out, the prediction for,
You said it was going to be lower, I'm sorry?
The torque required to achieve your clamp load would be higher if you were using a serrated.
So you'd say it would be up here somewhere.
Yeah, well, it'd be farther out, right? To achieve the same.
okay.
Let's see.
All right, in order to get just a yield, it took 290 inch-pounds of torque, and we got it up to 2,800 pounds of clamp.
So that's going to put us. So we can see that on this graph. Again, the brown line being the hex nut, the dark green line being your hex flange nut, and the light green line being your serrated hex flange nut, like Nathan just tested over here. So now our torque tension relationship has changed because we've added the serrations to affect the bearing surface. So if we're to pick a point on the graph, for instance, 100 inch-pounds of torque, we're only going to be creating about 1,100 pounds of clamp load, versus with the other two, we get much higher clamp load at that same torque. Now, if friction accounts for 90% of the torque, what would happen if your friction was reduced by 20%? What if you make something, what if you take friction away and make something more slippery, more lubricious?
You get more clamp load out of less torque.
Okay. So for instance, if we were to take our, again, our U sub 1 is our coefficient of friction. If we were to reduce that by 20% and keep the same torque right here, we should create more clamp load in the joint, which in a lot of cases is not a desirable effect. You obviously don't want to overstress a fastener or overstress your joint. So again, the correct way is to use your new coefficient of friction, go back to your original clamp load you want to aim for, and adjust your torque. So now we've adjusted the torque down right here. So if we use an oily part, kind of what we just talked about, what would happen to our torque tension then? If we had a part that was real slippery with a real low coefficient of friction. That'd be higher than the chart, lower than the chart.
Yeah.
Let's see what Nathan gets.
Okay, this part is another 1/4 grade 5 hex cap screw zinc plating, but I've added some synthetic light oil to it. This time, we got up to 160 inch-pounds of torque, which is about where the grade 5 was for torque.
Right.
But we now got up to 3,600 pounds of clamp, which is quite a bit higher.
we'd have to look at it. It's not a stronger fastener, but we'd have to discuss that a little more. It's not a stronger fastener. We'll talk a little bit about how it's going to affect the ultimate tensile strength a little bit in this slide here, which might explain part of that reason right there. So if we look at the effects of lubrication, again, we've got the dark green is just your zinc plated, your dry fastener, and a zinc plated with oil on here. You can see our oily fastener now has reached up to 3,500 pounds of tension, while our dry fastener only reached about 2,800 pounds right there. Why do we think those are different? What would be a reason for the difference? Again, these are both grade 5s. The heat treat hasn't changed, same lot of parts. Only difference between what is dry and what is oily.
Some of the oil is still in. Right?
A little bit. We didn't really talk too much about this. We touched on it a little bit earlier on. In a straight tensile test, where you're just applying tensile forces to the joint, there's no torsional strength, or no torsional forces acting on the fastener. And that's what your tensile strength and your specifications is based on. It's a straight tensile bolt. In a bolted joint like this, you've got both tension on your fastener, as well as torsional forces acting on it. So when you add oil to there, you reduce your coefficient of friction, you're taking away some of those torsional forces. When you take away your torsional forces, that allows your axial, or more of your fastener strength to be going to axial strength right here. So it's a little more complicated. It's something else we talk about a little more in depth, but in general, you only got so much of your strength to give between tensile strength and torsional strength. By removing some of the torsional forces in there, it allows it to get to a higher tension. We're going to talk a little bit about preload variation in fasteners right now. And again, this is a grade 5 zinc-plated hex cap screw. We tested 11 fasteners right here. Did the same thing Nathan just did, ran them all the way through the torque tension test right there. How come all these lines aren't exactly on top of one another? If the fasteners were heat treated and plated together, and there's really no other changes right there. How come these are kind of spread out like this?
Random deviation.
Exactly. Yep. It's just random deviation. It's one part might not be exactly the same. Microscopically as something else. Just random deviation, like Nathan said. So, what this shows you is that if you've got, for instance, perfect torque control, if you were going to assemble this joint to 100 inch-pounds of torque every single time, which in real life isn't generally possible, but say in theory you always assemble to 100 inch-pounds of torque, you're still going to get variation in clamp load in that, no matter what. So if you do everything perfectly, you're going to get this amount of variation. You can see that. Again, at 129 inch-pounds that we looked at earlier for our assembly torque, your variation in clamp load can range by as much as plus minus, or about 30% total variation. Talking a little more about variation and about how coating changes, or coating materials change the torque-tension relationship, as well as something else. You can see here the bottom green lines are zinc-plated, and then the top darker lines over there are for dip spin coatings right here. So you can see by changing your plating from a dip spin to a zinc, you've changed your coefficient of friction, you've changed your torque-tension relationship. You're now going to be able to apply more tension in your joint at a given clamp load than you would with the zinc. Which isn't too surprising considering what we've talked about so far today. What is a little different and is surprising is that what happened to our variation between these two at a given torque? How does our scatter look, Phoebe, between the two different coatings? Is it more variation or less variation or different? Yep. If you were to start out with a zinc-plated part in this and switch it to a dip spin coating here, in some cases you can actually tighten up your variation, your torque tension. On the flip side of that is if you've got a bunch of parts that are dip spin coated and you were to switch to a zinc plating and not take this into account, all of a sudden you've altered your torque tension relationship, but you've also added more scatter right here. So this helps illustrating how different changes in plating really affects what your joint is going to do. It has to be considered. You can't just necessarily swap between different fastener coatings and expect to get the same performance. So a little more about scatter over here. Like I mentioned before, perfect torque control is generally not possible. When you've got an assembly line, if you've got someone who's using an impact wrench or just a hand torque wrench, you're not going to hit that 100 inch-pounds every single time. You're going to get some variation in that assembly process. Maybe as high as 110 inch-pounds, maybe as low as 90, whatever that's going to be. If you add that variation into your variation of preload we looked about, you get a pretty big window of where your clamp load can fall. You know, your lowest case could be down here, or your highest case could be up here. In this case, PT is prevailing torque lock nut, which we've looked at here. If you were to have a lock nut with a lot of friction and a lock nut with a little bit of friction, it's really going to help, or it's really going to increase the amount of variation in your joint. So the main goal of this slide here is just to kind of show you that you want to reduce the amount of variation in your joint and not add extra features when you don't need it, or just extra items that might cause you to have more variation right here. The best joint is generally the simplest joint because it's the easiest to control. When you start adding things like lock nuts or lock washers and things like that that aren't always necessary in some cases. In some cases, you may just be adding more variables to your joint, which is going to increase your variation.
Is that torque control then?
Not necessarily. It depends. Your torque control is going to be dependent on your assembly method and your assembly tools. Right?
Well, but what you're illustrating, is that for torque control then, have that much variation?
The torque control, it would depend on what your method is right there. If you have like a torque to yield kind of gun, I would say this would be excessive for that. For a handheld torque wrench, that's probably in the ballpark. So all that math we did earlier with the long forms and all the variables, that does take a little bit of time. It takes some research to know what your variables are, know what your coefficient of friction is, know what your clamp load is. There is a little bit simpler way, and that's called the nut factor equation. And that's generated, or it's shown as T equals KdP, where T is your tightening torque, K is your torque coefficient, D is your fastener diameter, and P is the bolt's tensile load. So this is the shorthand version of the problems we were looking at earlier, and the math we looked at earlier. So what this is going to help us do, it's used for a few different things. It's used to help us calculate the K factor in your joint, which we mentioned was the torque coefficient. There are charts that show what that torque coefficient should be in general, but if you need a definite answer, you can use this formula to determine what your torque coefficient should be. It can also be used to calculate assembly torque of what you want to go to. If you know your preload you want, you know your torque coefficient, then you obviously want to know, what do I want to torque that joint to? That's where we use this formula. Going back on the slide. It could also be used to predict what your clamp load is going to be at your variation. So the previous slide we looked at had the 90 inch-pounds of torque and the 110. If you want to know how much clamp load am I going to get in both of those numbers, you can use this formula as well. It'll tell you what your clamp load is going to be lowest end and at the highest end. So if we walk through the steps again over here, we can switch this formula around to determine our torque coefficient just by swapping the characters around. In this case, we do a torque tension graph like Nathan just showed. We know our torque at 100 inch-pounds. Diameter is 250 because again it's a 1/4 screw. So your D is just your screw diameter of 250. And then 2,000 pounds of force. You can see that illustrated on the graph because your point is 100 inch-pounds versus your 2,000 pounds of force. Calculate that out, gives you a K factor of 0.2. And again, you can find some of this on charts, but for critical joints and when it's necessary, sometimes you want to run through the testing to figure out exactly what that's going to be. Now that we know our torque coefficient, we can flip this formula around again to look for our bolt preload, what we're going to do. So at 150 inch-pounds of torque, our 0.2 K factor we just determined, multiplied by our bolt diameter, gives us a preload of 3,000 pounds of force. So if you go back to the chart over here, 150 inch-pounds, if you carry that up, it's about 3,000 pounds of force right there. And you can do this for anywhere you wanted along the graph to determine where that is. So for example, if we had, again, our famous 1/4 quarter 20 by 1 hex head cap screw. The joint requires 2,200 pounds of clamp force. What torque should we specify for that joint? It's a pretty common question as engineers when you're designing a joint. We use, for our torque coefficient, we use 0.22. In this case, maybe it's not a critical joint, maybe it's just holding on something that's not a critical area. We can pull this number from the IFI website, plug that in, your 0.22 coefficient, torque coefficient, multiplied by your bolt diameter, multiplied by your necessary clamp load, gives you 121 inch-pounds of torque.
So what gave you the 0.22?
From the IFI website, they list charts that will show, the chart's generally shown by plating. So if you've got a zinc plated part, or if you've got a dip spin coated or Fastener oil, you're going to have a different torque coefficient for each type of plating.
So that's for zinc, is what you're saying?
I believe that's for zinc, yes. It should correspond with the plating up here, correct? So remember, if we did our last math problem on the same kind of part, ran through all of our numbers, we got 129 inch-pounds of torque. So again, this is just different methods of estimating. We had 121 with the short version, 129 with the long version here. Different methods of estimating what your torque is going to be. This method here takes more of the geometry into account, so that's where your subtle difference comes from right there. Now, a lot of people, when they're designing joints or want to figure out what do I tighten the screw down to, what's the first place they look to? If you hadn't had this class and didn't know any of this stuff, if you're going to go to assemble an engine and didn't know what torque to use, you'd probably go to the internet and look for just a web-based torque chart similar to this. Is this a good chart to use if you're trying to design a joint? Brendan, any ideas?
Depends.
What's missing from this chart, or what have we talked about previously that you really don't see called out or specified anywhere?
Any coatings or any differences in the part.
Exactly. They don't list any kind of different coatings. They just say quarter 20, grade 5 is this many foot-pounds right here. They don't mention coatings. It doesn't take into geometry into effect or the coefficient of friction. So it also doesn't show you what preload you're going to get with this fastener here. Maybe this is 90% of yield, maybe this is 50% of yield. We don't know because it doesn't specify what it is. So charts like this are pretty common. And generally, there's much better, more accurate ways to do it, just because you don't have all the information you need with these charts. Now, if we look at this chart, another one we found on the internet, is this chart better or worse, or is this okay to use? Nathan, any idea?
Looks better, it's got a lot more information on it. I can see lubricated, zinc plated, so they're identifying what finish it is. So
Right.
I'd say it's good.
It's a little better. In general, they've actually specified between lubricated, zinc, and plain. But again, the problem is they don't mention geometry, they don't mention head diameter. If you've got a part with a serrated bearing surface, this won't help you very much. These are also not very specific. Again, like I said, different platings give you different coefficient of frictions or torque coefficients. Just by, zinc plating might be common, but there's obviously many applications that don't use zinc plating. So again, it's a better chart. There's a lot of information on here. In some cases, this might be good enough. In many cases, you want something more accurate. So again, just to kind of summarize what we talked about with the torque charts right here, be cautious of what you're looking for. So it really depends on what you're trying to do, how critical your joint is, and whether or not you can use a web-based chart like that. We mentioned before, if you're putting a screw that's going to hold a nameplate on a wall, you could probably use the charts that are on the graph, the numbers that are on the charts, and you'd be okay. Versus a connecting rod bolt and an engine that's going to spin at 7,000 RPMs, you probably don't want to use those charts. You want to put a little more calculations and some testing into it. We talked earlier a little bit, John mentioned about whether or not that was a good amount of torque control, or if that was good torque control or bad torque control. That kind of relates back to this right here. These are different methods of tightening. Everything from an impact wrench or hand tightening. An impact wrench being like what your mechanic uses to take off your tires. versus yield point, which is a computer-controlled assembly method. DC electric divers are pretty common, or just your calibrated torque wrench right here. Your preload scatter is huge with your impact versus much better with your yield point control right here. So your assembly method actually plays a part into how much clamp load scatter you're going to get in the joint. And that makes sense. If your impact wrench is going to assemble a joint anywhere between 80 foot-pounds and 120, you're going to get a whole lot more scatter than you would if your yield point control assembles between 90 and 95 foot-pounds. So again, this is why torque control is so critical. Again, too much clamp load isn't good for your joints. Too little clamp load is also not good for your joints. Too much clamp load and you could yield the material, you could fracture the fastener, you could strip out the threads. Too little clamp load and your joint won't withstand the forces. It could come loose, it could fracture. It could also fracture the fastener in service. So why do fasteners fail? What makes, if I've got a joint on a car and it fails down the road, why did that fastener fail? You think that's bad heat treat or bad manufacturing, or is that seams or cracks or
Rust.
The director of the IFI estimates that about 90% of fastener failures comes from poor design quality, going back to poor torque control or poor assembly methods, or even speccing out the wrong fastener right there. Only about 10% from his estimation is into fastener manufacturing defects right there. Now, some possible fastener failures you can see. Insufficient preload from poor torque control. You also have improper hole preparation is another example. If you've got a clearance hole for your fastener that's too small, so you've got a 1/4 inch fastener and your clearance hole is actually 250 or less than that, it's going to make some interference with your threads right there. What's that going to do to your friction formulas right there? Okay. I'm going to increase that right there. Right? If it's unintended friction, if you don't plan for it, you've got that fastener going into that undersized hole, your friction is going to be thrown way off. And again, it's going to affect your torque tension. So what do you do when a joint fails? If you're an engineer in a building and one of your operators comes up and says, hey, I've got this on the assembly line down there, my boss is screaming at me, and I've got these parts that are breaking, every fifth part I just snap off right there. What's the normal first step in that case?
Make sure you're using the right part.
Yep. A lot of the times, and that's what you need to do, a lot of the times, the engineer is going to say, oh, this fastener's bad, this must be breaking, go check the heat treat, go talk to the supplier, go see there. What we've learned today from here is just to take a systematic approach and kind of go back. Look at your assembly process, look at your torque callouts. Was there a part substituted? Did the plating change? Did the holes change? Take a systematic approach to look for that root cause of why the fastener was failing. You want to avoid your initial conclusions. Again, it's not always the fastener failure itself due to material defects. And consider the torque tension effects. Like we mentioned, did something change recently? Did somebody switch out the fastener for something else they had in stock? Did they change the plating to get better corrosion and not affect not change your torque number? So consider the torque tension effects. Talking a little bit about fastener driving. Again, there could be, if you're having failures in the line, look at your assembly tools. Look at the torque, look at the RPM, look at your bit right there, look at the condition of it. Just adds to variations in your fastener process. Now again, you want to make sure that you've got the right amount of alignment, you're not coming in off angle. Different bits require end load. While some bits do require end load to stay engaged and some do not. A Phillips recess, obviously, you need to put some end load into the recess. You need to put some end load being pressure to keep that recess engaged right there. Versus a hex recess like this, or a Torx recess or a 6-volt, you don't need any end load, which is one of the benefits right there. So. Other considerations you want to look at, you You want to look at the recess or the head condition, and look at the lead or skirting threads. Generally, this is in cases of a tapping screw, not necessarily a machine screw and a nut, but if you had a tri-limbler screw or a tap tight, you want to look at the lead threads. Are these creating too much friction? You also want to look at the recess or the head conditions. Is your head oversized or undersized? A different size bearing surface will affect your torque-tension relationship as well. You want to look at your engagement material, the hardness of it. If someone were to make prototypes with a nice fancy machined casting and do all their testing with that, then the production parts come in and it's a die casting or it's cast iron, your surface finish might be a lot different. Did that affect your torque-tension relationship? Could that be one of the issues to look at? Also the hardness. If something is too soft, it will lead or can lead to more embedment in your joint, which will reduce your clamp load in the future. Again, we talked about clearance hole sizes. A clearance hole size that's too small will add friction to your joint. A clearance hole size that's too big it'll allow you to have less friction in your joint. So both directions can affect your torque-tension relationship. Again, look at the nut member. Are the threads undersized or oversized? We've seen a lot of cases where the hole's not tapped correctly, or the hole's tapped undersized. That's just going to increase your friction that you need to overcome with your fastener, which will affect your torque-tension relationship. And again, the hole size as well. You have too much chamfer, too little chamfer. So again, to summarize, torque is used to estimate the clamp load. It's usually the most cost-effective method, and it's what we've got to work with. And the variation in the process is okay, as long as we design for that variation and we account for it. And again, when investigating fastener failures, you want to use a systematic approach to that. You want to look at your process and not necessarily jump to conclusions and say, this fastener is bad. Look at your process, try to keep it as controlled as possible. And if you have any questions, please use Field as your engineering resource. Anybody have any questions today? Good. Thank you very much for coming today, and I appreciate everyone's time.